plugged in here really quick. All right, so some announcements. New homework is assigned. It's going to be over integration by parts. What we learned today. Okay. That's in Canvas. Announcement 2. I'm shooting for having exams graded by Friday, hopefully tomorrow, but more likely Friday because I have exams in other classes too. So I recognize that was a hard exam, and you're gonna have the chance to do corrections to get half the points back that you miss on the exam. Okay, so first of all, also if anyone has not had me before, hopefully you all know I'm a fairly lenient grader, but again, you're gonna get the chance to get at least get the half the points back that you missed on the exam. So corrections will be turned in by next Friday, and then as long as you get those corrections in, you'll get half the points back that you miss. Okay, any questions on that? Okay, cool beans. So today we're shifting gears and we're talking about techniques of integration, and I'll admit that it's a little bit it's not super applied. We're just trying to figure out how to do as many different integrals as we can. Okay, which is why I wanted to start the class with applications like volumes of revolution and some more applied problems, because those are more interesting. But learning different techniques of integration is very important. So today we're going to learn how to integrate something that looks like the integral of x times e to the x, which comes up all the time. If you tried to do this integral right now, you would not know how to do it, right? It's not a u substitution problem. There's no composition of functions happening here. What we need is the opposite of the product rule, right? Differentiation. I know how to differentiate this, x to the x. I don't know how to integrate a product of things that won't yield to a u substitution. Okay, so that's the whole idea behind integration by parts. Integration by parts is the opposite of the product rule. Okay, so let's refresh our memory on what the product rule is. If I have f of x and g of x are differentiable functions, then so is f of x times g of x. And we have f of x times g of x prime is equal to, what do I get when I take the derivative of f of x times g of x? Mark, what do we get when we take f of x times g of x prime?
Is it f prime times g of x?
Good.
Plus f of x times g prime.
Exactly right. This is the product rule for differentiation. Okay, that's exactly right. And so in type, there it is. So if I integrate both sides of this, well, when I integrate the left-hand side, I'm going to get the integral of f of x times g of x, that whole thing prime. What is the integral of f of x times g of x prime? April, what do you think? If I take the integral of the derivative of f of x times g of x, what should that give me? You're on mute. I think you said something, but
I was still thinking.
okay, no, that's fine. Sorry.
Is it going to be just it's not going to be just f of x times g of x, right?
No, that's exactly right. Yeah, that's perfect. Go with your intuition. We're all great mathematicians in here. Okay, so if I integrate a derivative, they undo each other, right? That's the whole point of an integral. Okay, on the right-hand side, when I take an integral, well, this one, I don't really get anything I can simplify at all. But this is the main idea behind integration by parts. Okay, so we get f of x times g of x is equal to the integral of, well, I'll just copy and paste this instead of writing everything out again. Copy, paste. My writing is so consistent. Okay. So you might say, well, I can't do anything with the stuff on the right, so who cares? Well, the idea is maybe f of x times g prime of x, maybe that's hard to integrate. But what if f prime of x times g of x, what if that's easy to integrate? Okay, that's the whole idea, is if we can sort of swap which function has the prime, that might give me an easier integral. Okay, that's the whole idea behind integration by parts. Okay, so the idea is, if I rearrange it, if I want to find the integral of f of x times g prime of x with respect to x, if I want to find this integral, well, I can take, apparently, f of x times g of x, I can just subtract this integral from both sides, right? So this is f of x times g of x minus the integral of f prime of x, g of x, dx. Okay, this is integration by parts. And it might seem not very useful as it's written right now. It's one of the most important integration techniques. If something doesn't yield to u substitution right away, my next guess is usually integration by parts. Okay. So this, again, I mean, we're done. That's it. Pack it up. We've learned integration by parts. Okay. Usually we rewrite this as, oops, oh gosh, what was that? No, go away. Don't, FERPA. There we go. Usually we rewrite this as, if I let u be f of x, this is not a u substitution, what I'm doing right now. This is me sort of shortening some notation. If I let u be f of x and v be g of x, then du is f prime of x dx and dv is g prime of x dx. And so notice that if I put some parentheses around or some circles around some certain things, this is the integral of u, and g prime of x dx is dv. That equals f of x is u, g of x is v, and this is minus the integral of, well, g of x is, again, v, so I'm going to write that here, and f prime of x dx is du. Okay, so this is the way almost everyone usually writes it, is the integral of u dv is equal to u times v minus the integral of v du. Okay. So when I say integration by parts, most people think of this. Okay. So if you want to think of it as in terms of F's and G's, that's totally fine, but I'm going to be using this. So just so everyone knows. So that's just me explaining how we got to the U's and V's. A reminder, what I did here is not really a U substitution. It's a way to shorten the notation so I don't have to keep writing F f of x and g prime of x dx. It's a much shorter way to write out integration by parts. So any questions about, again, I mean, this is it. This is what we're talking about for the next 2 days. These notes are going to take us through the end of class tomorrow, okay? So let's look at an application. Let's do that integral that we didn't know how to do before. We want to do the integral of x e to the x dx. All right. The hard part of integration by parts is deciding what function should be u, because this is the integral of u dv. We want, and then we want to rewrite this as uv minus the integral of v du, right? We want to pick what function is u, and then what we pick to be u, everything else is going to be dv. Okay, so we really have a couple of choices for u. The two obvious choices for u are u equals x or u equals e to the x. I'm going to tell you later a rule of thumb for how to pick what u should be. I'm going to tell you right now that if you pick u to be x, then dv is going to be everything else. dv is going to be e to the x dx. This is the right choice that you should make for integration by parts with this function. And again, I'm going to tell you how to get a rule of thumb for how to make these choices after this example. Okay. But if u is x, then what is du?
EX.
Yeah, one combining is one dx, right? Exactly right. And if dv is e to the x dx, then what is v? So we differentiate to get from here to here. To go from here to here, I'm going to take an integral. So here I took a derivative. Here I take the antiderivative of e to the x, and I get what? E to the x, perfect. And this is everything we need to do integration by parts now, okay? So again, this is the integral of u dv. Well, that is u times v, so x is u times e to the x is v, minus the integral of v, which is e to the x, du, which is just 1 times dx is dx, right? And now, and this is the whole reason we use integration by parts, the integral of e to the x is very easy to do, right? So this is scratch work. Scratch. This then gives us x e to the x minus, well, what's the integral of e to the x? We just did that. We did that in our work for integration by parts. It's e to the x. And then don't forget, this is an indefinite integral, so I need to add a c. So we just showed that the integral of x times e to the x is x times e to the x minus e to the x plus some constant. Or if you want to rewrite this as x minus 1 times e to the x plus c, that's also fine. But that's the real power of integration by parts. It swaps, it takes an integral that's hard to do and turns it into another integral that's hopefully a lot easier to do. And you can see, even with this example, that that choice of u is very important. If I had made the opposite choice, if I had chosen u to be e to the x and dv to be x dx, well, then the integral here would have actually been harder to evaluate. It would have been x squared, the integral of x squared e to the x dx. Okay, so we're going to learn how to make that choice of what should u be and what should dv be. Okay. But if you differentiate this function here, x minus 1 e to the x, you'll find that you get x e to the x. Okay, so are there any questions on this example? This is really, when you boil it down, all integration by parts problems. Now, this is one of the easiest ones, but we're going to look at some harder ones. But first, a very natural question that arises is, how do I pick u and how do I pick dv? Okay. Most books teach you the following acronym: LIATE. You look at an integral that uses integration by parts and you scream LIATE at it. Or some other books leave out the I. I'm going to tell you what the I means in a minute, but some books just teach the acronym LATE. And I could say that that's why I was late to class today. I was trying to drive home a point, but that's not true. I had car trouble. Okay. But I teach the I because LIATE is a funny word. Okay, so here's what LIATE means, or here's how you're going to use LIATE. When you're using LIATE to do an integral that looks like the integral of u dv, you're going to pick u to be whatever function appears furthest to the left in LIATE. Okay, so LIATE stands for the following. The L stands for logarithms. If you have a logarithm in your integral, well, I want that to be u. I definitely don't want the logarithm to be in dv, because we don't really know how to integrate most functions that have logarithms in them. So if there's an integral, something that's like the integral of x times the natural log of x dx, well, I have two possibilities for u, right? I could choose u to be x, or I could choose u to be natural log of x. Natural log of x appears furthest to the left in LIATE. So I would choose u to be natural log of x and dv to be x dx, and go from there. We're actually going to do this example after these slides, after this page. Okay. So there's L. I stands for inverse trig functions: arcsine, arccosine, arctangent. If you have any of these appearing in an integral that doesn't have a logarithm in it, then you're going to pick u to be one of those things. Okay. So for instance, in the integral of x times the arctangent of x, well, arctangent is the thing that occurs furthest to the left. That's an I. The x, we're going to find out, falls under the A category. Okay, so you would pick u to be arctan, dv to be x dx in this example. Okay. A stands for algebraic functions. These are combinations of x's to powers, sums and differences of those, along with square roots and all roots. Okay, so A, if I have the integral of, say, in that very first example, x e to the x dx, well, we're going to see what category e to the x falls under. I think you can probably guess what e to the x falls under, but x falls under this A category, an algebraic function. And so we would take u to be x and dv to be e to the x dx. Okay, just like we did in that first example. Okay. So when we just saw that one, if we had made the opposite choice, if we had chosen u to be e to the x, that actually would have given us a harder integral to evaluate. T stands for trig functions. Okay. So if we have the integral of, I don't know, sine of x times e to the x dx. Well, I have two options for u. I could have u be sine of x, or I could have u be e to the x. The e is going to be, e to the x is going to be in this last letter. So you choose the trig function to be u, okay? And Liotte, E stands for exponential functions. Okay, the point of this acronym, choosing U to be the thing that occurs furthest to the left, is as we go from right to left, well, really, as we go from left to right in Liotte, I really am picking the thing that is hardest to integrate, and I'm making that the thing I differentiate, right? I don't want to have to integrate logarithms, so I choose that to be u, the thing I'm going to differentiate. I don't want to have to integrate inverse trig functions, so I choose that to be u if that's the thing that's occurring furthest to the left, okay? This is how we use Liotte. Other books use the acronym detail and detail. And this is just Liotte backwards with a D in front of it. So detail tells you not what you should make U, but what you should make DV, right? You just choose the thing that's happening furthest to the left. In detail, you choose that to be DV. So that's where the D here is coming from. It's telling you what to make DV, okay? I'm gonna stick to Liotte. 90% of the time, Liotte will not lead you astray. Detail is the same way, but I'm gonna give you one acronym to use, Liotte. Okay. So let's do an example. Here we go. We want to find the integral of x times the natural log of x dx. So this looks like the integral of u times dv, and we want to find out what should u be. Okay. So when finding what u should be, I use Liotte. So what do we think u should be?
The natural log of x.
Exactly right. U should be, well, the furthest left is the natural log, right? That means dv should be everything else, x dx. When you're done choosing what u and dv should be, there should be nothing left to pick from. There should be no leftover stuff in the integral, okay? U and dv have to account for everything. Okay, so if u is natural log of x, then what is du? 1 over x dx. Very good. And again, in Liotte, this is why the logarithms are so far to the left, because you have a nasty function that has actually a really nice derivative. So that's why we choose u to be natural log. Okay, and if dv is x dx, then what is v? X squared over 2. Remember, you're just taking an indefinite integral to get v. Now you might ask, do I have to add the c here if I'm taking an indefinite integral? And the answer is no, you don't have to, and most people don't. It actually wouldn't be wrong to put it there, but you don't have to add the constant, and most people don't, as long as you add the constant at the very end of one of these problems. So we know the integral of u dv, integration by parts. This is u v minus the integral of v du, right? We picked u to be natural log of x, dv to be x dx. So this is going to give me u is natural log of x times v, well, that's times x squared over 2, minus the integral of v du, well, that's going to give me x squared over 2 times du is 1 over x dx. Okay. So that 1 over x cancels with one of the x's and x squared. And this becomes x squared over 2 natural log of x minus the integral of x over 2 dx. Okay. Which is x squared over 2 natural log of x minus the integral of x over 2. Well, you can pull that 1/2 out in front. And then the integral of x is, again, we did that before. That's x squared over 2. Okay. And now I will add my constant of integration. So this is x squared over 2 natural log of x minus x squared over 4 plus some constant. Yeah.
So if you switch, so like you switch to U and DB.
Yeah.
You would still get the right answer, but it'll just be.
Yes, it's the same. Yeah, good question. So the question is, what would happen if I made the wrong choice, quote unquote, for U and DB? What if I swapped those? Integration by parts still gives you a correct thing. It's just like with volumes of revolution. If you picked the harder way to do a problem, if you picked shells instead of washers when washers are easier, you still get an integral that's right. You still get an integral that gives you the right thing. It just might be very, very difficult to evaluate. And that's what happens here. If you chose U to be x instead of natural log of x and dv to be natural log of x, at that point, hopefully you would recognize, well, I don't know the integral of just natural log. So hopefully that would convince you I should make the opposite choice. But if you were able to do it, you still would get something that technically is correct. It just doesn't help us to find the final answer we want, right? Yeah, good question. Any other questions on this? And really quick, you should always verify that the derivative of your final answer gives you the original thing we were integrating. So the derivative of x squared over 2 natural log of x minus x squared over 4 plus some constant is, well, by the product rule, I'm going to get derivative of x squared over 2 is just x. Then I'll leave natural log of x alone. And then plus, I'll leave x squared over 2 alone. I'll multiply by the derivative of natural log of x. And then I'll take minus the derivative of x squared over 4. Well, that's x over 2. And then the derivative of a constant is 0. And so this gives me x natural log of x plus x over 2 minus x over 2, which is plus 0. And we get exactly the thing that we wanted to integrate. If I differentiate it, I get that thing back, which tells me that we're right, that we got the right answer of x squared over 2 natural log of x minus x squared over 4 plus a constant. Okay. So this is verification that this isn't just magic. This is good, solid rule. Okay. So let's look at an example that at first glance doesn't look like it falls under this integration by parts regime, I guess, if you will. It doesn't seem like integration by parts should work on this. And this example was the first one where I was like, oh man, this is some real powerful stuff. Okay. So I look at this example and I scream again, Liate. So this is, apparently I'm telling you that this integral still looks like the integral of u dv, right? So with Liate, what would I pick u to be? I would pick u to be natural log of x. What does that force dv to be? Yeah, perfect. Just dx. dv is dx. You see that? When u is this, that means dv has to just be dx, or 1 times dx, if you will. Okay. All right, so if u is natural log of x, well, just like last time, that means du is 1 over x dx. And that means v, if dv is dx, then what is v? X, perfect, exactly right. So we're doing the integral of u dv. This is, by integration by parts, u times v minus the integral of v times du, or just v du, if you will. So this is, well, u times v is x times the natural log of x minus the integral of v du. Well, that's minus the integral of x times 1 over x dx. Well, x times 1 over x is just 1. So we get x natural log of x minus, what's the integral of just 1 dx? X, perfect. And then don't forget, with these indefinite integral problems, you need to add a constant at the end. But that is the integral of natural log of x, is x natural log of x minus x plus a constant. Okay. So, questions on that? All right. This one. Oh, this one. Here we go. So you look at this integral and you scream Liate, because this apparently looks like the integral of some function times some other function. We could try a u substitution, right? But there's not really a composition of functions happening here. A u substitution would not be super helpful for this one. So instead, we're going to do integration by parts. So that means I need to pick a u, not that's a u substitution, but my u for integration by parts. So what should u be? I want to pick the thing that's farthest to the left in Liate. So what should u be? X squared, that's exactly right. I have an algebraic function here in x squared and a trig function here in sine of x. Well, algebraic functions come further left in Liate than trig functions do, right? So I'm going to pick u to be x squared and dv to be sine of x dx. Okay. Then what is du? 2x dx, perfect. And what is v? Perfect, exactly right. Negative cosine of x. Very good. So this is the integral of u dv is, again, uv minus the integral of v du. I'm going to say that at least 10,000 times over the next couple days. So u times v, well, that's negative x squared times the cosine of x. U times v. Minus the integral of v du. Well, v du is negative 2x cosine x dx. And so constants I can pull out in front. So this is really going to become plus 2 times that integral of x times cosine of x, right? Questions on what we've done so far? Now, these types of problems, every Calc 2 student hates them. How do I do this integral? Yeah, it's this is actually another integration by parts problem. So now I need to do, I'm looking at the integral of x cosine of x dx equals, well, this is also the integral of u dv. So I do another integration by parts. What is u now? Well, again, remember Liate. Yes, Liate. U is now x. I still have an algebraic function happening here. So u is going to be x. dv is going to be everything else. Cosine of x dx. So if u is x, then du is what? 1 dx. Perfect. And if dv is cosine of x, then what is v? Sine of x. Perfect. All right, so this new integral that we got, that we need to evaluate along the way to get our original integral, this new integral becomes, well, again, this is u times v, so x times sine of x, that's uv, minus the integral of v du, well, that's minus the integral of sine of x dx. So scratch work. But what is the integral of sine of x dx? Good. So this is going to give me x sine of x minus negative cosine of x. Or in other words, I can just write plus cosine of x. Plus, I can do the plus c here. I'm going to wait until the very, very end. Because remember, we were doing this on the way to getting our original integral. So I need to take this and plug it back in here, right? For that integral. So this tells me that my original integral, the integral of x squared sine of x dx, this is, well, I come back here, I have this stuff, negative x squared times the cosine of x plus 2 times, and then the integral of x cosine of x, we did another integration by parts to find that. And so that's going to be x sine of x plus cosine of x. And this is why, if you want to plug in the c here, you can, but then you're going to get 2 times c, which is just another constant. So I usually just write the c out here. And so this is a case where you had to use integration by parts 2 times to do one integral. And that comes up pretty frequently. And doing it this way, writing out u and dv every time can be annoying. But this type of problem where you have some power of x times a trig function or some power of x times an exponential function, there's a very quick way to do those that I'll talk about tomorrow that involves, it's called tabular integration, but it involves making a big table and then eventually you just sort of do some cross multiplying, and it's much easier to do that than to keep writing out integration by parts and integration by parts and integration by parts and so on and so on and so on. Okay. But integration by parts did give us a way to evaluate an integral that we would have had 0 chance of evaluating before. Okay. So are there any questions about this example or integration by parts in general so far? Okay. Example. Oh, look at that. I gave you a warning. This one is a trick. Don't fall for it. trick is a little strong. This is still an integration by parts problem. Let me be clear about that. But let's look at, let's forget I hadn't, let's forget I had warned you about this really quick, and let's look at this. This definitely looks like the integral of u dv, right? And if I write out Liate, then what would I pick u to be? And what would I pick dv to be? Yeah, yeah, exactly. Just following the rule of thumb I gave you, Liate, u would be t cubed, dv would be e to the t squared, dv would have to be everything that's left, e to the t squared dt, right? So I could find du, but first let's look at how would you try to find dv? Well, you would integrate. Remember, to go from u to du, I take a derivative. I take a prime. To go from dv to v, you take an indefinite integral. So does anyone know what the indefinite integral of e to the t squared is? That's the derivative. That's going the other way. Careful. So this would be, yeah, careful. This is the whole point of this problem is you can't, whatever anyone had said, I should have stopped you right away because no matter what anyone says, it's wrong. No one can do this integral in a simple closed form. There's a way at the very end of this semester, we're going to talk about a way that you can sort of write an answer to the integral of e to the t squared, but it involves sums and it's not just a simple thing. So the short answer is Liate has led us a little bit astray here. The integral of e to the t squared, we can't do it, even with integration by parts, even with all of the techniques we know. So the trick is, and you hinted at this, what is the derivative of e to the t squared? Well, you said it already. It's e or 2t times e to the t squared, right? So I know if I integrate 2t times e to the t squared, I know that integral, right? That's the trick for this one. I don't know the integral of e to the t squared. I do know the integral of t e to the t squared. Okay, so I'm going to borrow one of the t's from t cubed, and then I'll make u t squared. Okay. So most of the time, Liate won't lead us astray. Sometimes we run into situations like this, where the need to be able to integrate dv is going to force us to pick something slightly different than what we normally would. Okay, I can't integrate e to the t squared. You can't integrate e to the t squared. Einstein couldn't integrate e to the t squared. You can't just write a simple answer. Okay, but we can integrate t e to the t squared. Okay? So that's why in this case I would pick u to be t squared and dv to be t e to the t squared. Really, I would pick dv first to be the thing that I know how to integrate. Okay? So if u is t squared, then what is du? 2t dt. Excellent. And then what is the integral of t e to the t squared? Careful. So the integral of t e to the t squared, if we didn't know about integration by parts, how would you do this integral? Yeah, this is a u substitution, right? You would let u be t squared, and then du is 2t dt, which means that 1/2 du is t dt, right? And that means the integral of t e to the t squared, well, that's 1/2 times the integral of e to the u du when you plug in your u substitution. which is 1/2 times e to the u plus some constant. I mean, I'm telling you explicitly, I'm ignoring the constant for this because I'm going to not care about the constant when I write it for v. And this is 1/2 times e to the t squared. So v is 1/2 e to the t squared. So this one it takes a lot of thinking to try and make a very clever pick for u in dv. So let's write this out then. This is u times v minus the integral of v du. Well, u times v, that's going to give me 1/2 t squared e to the t squared. 1/2 t squared e to the t squared. Minus the integral of v du. Well, that's going to be 1/2 e to the t squared times 2t dt is just going to give me 1/2 times 2 is 1. So I just get t e to the t squared dt. Okay. And then we just did that integral before, right? We did this integral right here. We know that's 1/2 e to the t squared again. So this is 1/2 t squared e to the t squared minus 1/2 e to the t squared plus some constant. Okay. Again, this is a very tricky integral. I wouldn't throw this one at you on an exam. This one is, I would give this one to you as like a week-long project to try and walk you through the steps of getting this. But this is a very tricky integral. You need to be very careful when you're picking u and dv. Most of the time, Liate, again, will give you exactly what you want. I do need to show you examples where Liate doesn't quite work the way we want it to, and this is one of them. Okay. So with that, we're going to stop there. Tomorrow, we're going to look at one of my favorite integrals, the integral of sine of the natural log of x. And then we'll start talking about integration by parts for definite integrals. And that will be really everything we need to know about integration by parts. Okay, so tomorrow we're going to pick up here, same notes, and go from there. All right. So thank you all for being here. If you have any questions, remember I have office hours today, 10 to 12. But other than that, feel free to head out, and I'll see everybody tomorrow.
Thank you.
Thank you.
Thank you.